Okay, so in this lecture, we're going to kind of continue our discussion of transition metal reactions, obviously, and we want to focus on sort of the next things to count or consider when you're studying transition metal complexes. And they are, well, let's first recap what we've already studied. So after knowing how to determine the total number of electrons, after determining the total electron count, we want to also, in step 2, determine the transition metal oxidation state. As well as 3, we want to determine the d-electrons on the metal. Okay, and both of these kind of go hand in hand, and they start with a good understanding of what the ligands are doing to the electron count on the molecule. So to determine the oxidation state, this is a little bit of a formula. Okay, for the oxidation state, we want to take the overall complex charge and this is usually 0. Sometimes you can have a transition metal complex that's overall +1 or -1 or something. We should keep that in mind, but often this is 0. And you want to then subtract from that the charge from, let me see if, the charge from monovalent ligands, monovalent, and I'm gonna put this in parentheses, monovalent, divalent, and maybe even trivalent ligands. Okay, so let's look at an example of this. The molecule titanium tetrachloride is shown here. It's overall 0. So I'm going to put a bracket around, and that signifies that the complex charge is 0. So what about the charge from the ligands? Well, what we have is we have 4 times a monovalent ligand. Monovalent ligands are ligands that when they absorb the electrons from the transition metal, they would give something that's -1 charged. So that's like having 4 times a -1 charged attached to our titanium. So what we do is we take the complex charge, which is 0, minus, and then we're going to subtract from that -4, because 4 times -1 is -4. So that's going to give us our oxidation state of titanium in titanium tetrachloride. Well, in this case, 0 minus a -4 is equal to +4. So we could write titanium +4 as the central atom in our titanium tetrachloride. Or we could write titanium Roman numeral 4 chloride, but everybody sort of calls it titanium tetrachloride. That way you can call it by a name that makes everybody uncomfortable. You can shorthand it as Tickle 4 instead of titanium tetrachloride. So Tickle 4. Gross in my mind. Okay, anyway, so that's titanium tetrachloride. And what we've done is we've said that in the complex titanium tetrachloride, sorry, I have to make a new page. In the complex titanium tetrachloride, we have a titanium 4 element. We could say it this way. Whoops, I broke my thing here. So titanium tetrachloride has a titanium +4 as the oxidation state. The total electron count is, well, if we look at our periodic table, I'm going to pull one up quick. So titanium is in 4 if palladium is 10. So titanium gives us 4. And then we have chlorine gives us 1 each, and we have 4 of those. So our total electron count is a measly 8. And so this is pretty far away from the octet rule, and you would expect this to be reactive. And indeed, it smokes at you when you pull it out. Now let's take a second look at the oxidation state. So the +4 sort of told us how we're able to achieve a neutral charge in the complex. We have 4 -1 charged chlorine atoms attached to this complex, and we have then a metal, if it's going to be overall neutral, has an oxidation state of +4. The metal itself has inherently a +4 charge. Okay, that's what that means. So titanium tetrachloride has an oxidation state of +4. And we could look at another example. Let's pick on ferrocene. Ferrocene's a great example. So titanium tetrachloride kind of smoked at you. You typically buy it diluted in a solvent. You don't want to handle it neat because it's just going to go bad so quickly, but it's a super great Lewis acid. But what about ferrocene? So ferrocene is this sort of metallocene or metallo-sandwich complex where we show the iron having lines to circles that are around the pentagons. Now, each of these pentagons is a cyclopentadiene anion ligand. Now, another way of thinking about this is it's like the iron is adducted to 1 carbon of the cyclopentene. I'm going to draw the cyclopentene anion. So this is aromatic. We've talked about this in several contexts, but we've got a monovalent interaction with a negatively charged carbon atom, and then 2 pi complexes. The monovalent interaction provides 1 electron. The 2 pi complexes provide 2 electrons each, so we get 4 electrons from the pi complexes, which means if we have, and CP is the abbreviation for cyclopentadiene, if we have a monovalent interaction plus 2 pi bonds, or pi complexes, 2 pi complexes to our transition metal, we then have 5 electrons total from CP. Okay, now another way of writing that is we could say, well, it's just eta 5 CP, which means it's simultaneously adducted to all 5 atoms. And if we have eta 5, that's that eta number, that hapto number is what it's called. That tells us exactly how many electrons this ligand is going to give our transition metal. So we get 5 electrons from our transition metal. Well, I already showed that that's also the same number that you would come up with 1 monovalent interaction and 2 pi complexes. If you had benzene, I said that could be eta 6, where you're, and another way of thinking about it is you form 3 pi complexes to the transition metal, which gives you 6 electrons total. There's a few ways of thinking about it. The reality is it's simultaneously sort of interacting with all 5 atoms equally. So eta 5 is most correct. And that's because the negative charge can bounce around the ring. It's aromatic. All the carbon atoms are the same. So we have 5 electrons per CP. So the total electron count we're going to use the neutral atom approach. Total electron count is, we have 2 times 5 electrons from the ligands, and that's because we have 2 CP ligands. So 2 times 5 plus, looking at my periodic table, if palladium is 10, we're going back 2 rows to iron, which is 8. So we have 2 times 5 plus 8. Now, if you recall, this stuff is like ultra stable. It's hard to like even do chemistry on it. We had to do a Friedel-Crafts reaction, which means we got back our aromaticity. So we have 2 times 5 plus 8. That's equal to 18 electrons. So unlike the titanium tetrachloride or the Tickel chloride, to make everyone uncomfortable, unlike Tickel chloride, we're at the 18 electron rule, whereas before we were at like a classic octet rule and the stuff was smoky on us. This stuff is going to be rock stable. In fact, the person that discovered it was known for carrying it around conferences. They were so proud of this molecule. I would be too. It's a pretty crazy structure. Anyway, let's go ahead and look at the oxidation state of the iron atom to see if we can draw any similarities. So Cp has a -1 charge. Okay, and it's from that, if you want to think about it as not being 8 of 5, it's got that one monovalent ligand on it. So this is going, and if we have 2 of these, the iron has 2 -1 charged ligands. And if iron has 2 -1 charged ligands, iron must be +2 to make a neutral Ferrocene complex. Let's clean that up. Okay, so iron has to be +2. And said another way, we've got our ligands. They have a -1 charge. The overall charge in the complex is 0. So complex charge minus total ligand charge, or the sum ligand charge in this case, is equal to our oxidation state, which I'll put as OS. We have 0 minus -2 for having 2 -1 charge ligands. That's equal to +2 on the oxidation state. So iron has +2 oxidation state. Okay, we could do more examples of these, but before we do, let's move on to the next item that we want to look at, and that's the d-electron count. So the d-electron count is the third thing we want to be able to know or recognize or determine about our transition metal. The d-electron count, that is the number of d-electrons on the metal. Okay, just checking my notes to make sure I have this right. It always kind of evades my senses when I first look at this after teaching this class for 2 years. But I believe we just take the neutral element number or the group number, and we subtract the oxidation state number. So this is going to be the neutral atom number minus the oxidation state number. I think that's true for the most part. Okay, so we're going to take the neutral atom number minus the oxidation state number. So if we look at Fe2+, which is the iron that we had in our ferrocene, which we said had 18 electrons and then an oxidation state of +2, we would say the neutral atom has 8 electrons. That's its group number. And if you forget, the neutral atom palladium has 10 is in group 10. So we take 8 electrons minus a +2, that's equal to 6 electrons, and its d-electrons in the iron of ferrocene. So those are the three things I want us to be able to look at. So before we break, I want to take a second to look at some of these and see if we can figure out how many electrons that we have total. So let's go back to titanium, for example. So let's say we have titanium and it's adducted to a trimethylphosphine, an ultra-toxic version compared to triphenylphosphine, and we have a couple of CPs. So this is a known transition metal complex. So CP is cyclopentadiene. Trimethylphosphine is just P with 3 lines hanging off of it. I could make these methyls if you like. Think of it as like triphenylphosphine. Again, it's a little bit more toxic, volatile, harder to deal with. So if we looked at the, I'll write it over here, the OS on our titanium, well, we have 2 -1 CP ligands, so that's an OS of +2. So we have 2 times CP. So cyclopentadiene has a monovalent point on it. I mean, it's just inherently a -1 charged ligand that when it binds to a metal, we have to accommodate that if we're going to get to an overall neutral complex. And I should have written my bracket with a 0 over it to indicate that. The d-electron count on this is then going to be, well, we're titanium group 4 minus the oxidation state of +2. That's going to give us 2 d-electrons. And that's because we have a +4 for the group number minus 2 for the oxidation state gives us a 2 d-electrons total. Okay, now our total electrons. This is what I really like to pay attention to. It's all important, but I should tell you, I really like to pay attention to the total electron count. Okay, so we have 4 electrons, and this is from our titanium. We have 2 times 5 electrons. These come from our CP ligands, and we've talked about this. Now, what about trimethylphosphine? It's just like triphenylphosphine. Trimethylphosphine is a Lewis base. And if it's a Lewis base, it provides a lone pair through a Lewis base interaction with the transition metal. So we're going to take 2 times 2 electrons, and this is from the PME3. I'll even highlight the lone pair there. And I could even put the -1 on the CP and the +2 on the titanium just so we can see what everything's kind of charged when it's by itself. Okay, so we have 2 times 2 is 4. We have 2 times 5 is 10, and we have +4. That gives us, no. That gives us, no, that gives us 18 electrons, yeah. 18 electrons total. Okay, so we have 18 electrons total from this interesting titanium complex, right? Because 2 times 2, I'm just checking my math. Okay. All right, so we could then do some interesting chemistry on this, which we could talk about later, but the interesting chemistry, well, we could talk about it now, sure, because it'll give us some practice counting electrons. Let's say we have titanium, and we have a PME3 and a PME3 and a CP and a CP. Well, this does an interesting reaction where if we have 18 electrons here, we can actually dissociate one of the electrons. So this is called Ligand Dissociation. And what I do is I just draw a curly arrow going to the ligand. But if we start +2, note that we don't actually change the charge or the oxidation state on the metal. We're still at +2. And if we don't change the oxidation state, we actually don't change the d-electron count. But our total electrons go from 18 to 16 electrons, 4 on titanium, 2 on trimethylphosphine, and then 10 from the CP ligands. Okay? So we have 16 electrons total here. And then what we do is a ligand association. It turns out here we're going to make a pi complex to an alkene. So these are kind of the first reactions that we'll do. And we'll look at these in more detail. I'm just giving you a sense of sort of electron counting. But this is the first, you could call this a ligand exchange process, but there's 2 fundamental reactions that we're seeing. We're first seeing the ligands dissociate to get to something that's 16 electrons, and this is reactive. And remember, we're focused on the things that facilitate the reaction, not the end product being stable. So when we start, we start with 18 electrons. It's stable. We can put it into a flask. Big deal. It's not going to do any chemistry until we drop down and away from that 18 electron total. So we do that by having a ligand dissociation event, which makes room for a new ligand to come in. And now we have something with some carbon atoms that aren't aromatic, and we can start to do some chemistry. In this final complex, we now have Cp times 2. That's going to give us 10 electrons. We've talked about that. PMe3, which gives us 2 electrons. We've talked about that. And then we've got a pi complex from the alkene, and that's going to give us 2 electrons. And then we have titanium, which is going to give us 4 electrons, and we're back to 18 electrons. So it's nice. We could associate a new ligand to do something interesting. And the reason why we did that was to get back to this 18 electron rule. Okay, so we've got something that's thermodynamically stable and now has some interesting carbon atoms. I'm going to make note that this event is called a ligand association. What I want you to note, though, is that in every case, the titanium actually didn't change its oxidation state. It stayed at +2 the entire time. That's because we didn't lose like a monovalent ligand. That's actually kind of harder to do. And we'll actually talk about the reactions later. I want to focus on the electron counting. But the d-electron count didn't change, and the oxidation state didn't change, even when we were losing ligands, and that was because they happened to be Lewis-base ligands in this case. But this is a really kind of important process that happens quite a bit. And so this ligand dissociation, reassociation. And one in particular is kind of the old school tetrakis, which is actually the shorthand for palladium tetrakis triphenylphosphine, where it's palladium with 3 triphenylphosphine ligands around it. And we know that this, if we look at this, let's look at this. We have an oxidation state equal to 0. Why is it palladium 0? Well, if you look, none of the ligands would provide charge if they weren't bound to the transition metal. They're all Lewis bases, these phosphines. So we have a 0 oxidation state. If we have 0 oxidation state, the electron count is 10 electrons total. That just matches the neutral atom count number. And then the total electrons are, well, we have 10 electrons from palladium in its neutral atom form, and that happens to be the form we're using this time, and we have 4 times ppH3, which is going to give us 8, because each of those provides 2 electrons. So 10 plus 8 is 18 electrons total. So triphenylphosphine is a really robust reagent and is often used in reactions that are catalyzed by the intermediacy of some other palladium source. Oftentimes people will call this a pre-catalyst, because the first thing that it does before it can actually undergo a reaction is lose or dissociate one of its triphenylphosphine ligands. That allows us to go from a palladium in the 0 oxidation state with 10 d-electrons to a palladium in the 0 oxidation state with 10 electrons. But the difference now is we go from having all of that with 18 electrons to now having 16 electrons. And we can then associate another ligand. I think it's important to spend some time here just practicing complexes. So as you're sort of getting used to these electron countings, the goal is really just to look at more and more metal complexes, and they can be even weirder. So I've got some examples here. Let's go with ruthenium attached to a CO ligand, a ppH3, and the this image that I'm following has some geometry, which is always helpful. And this is going to be, it's an ugly allyl group. Let's just go ahead and draw the allyl group here. So this is just indicating that we have an allyl ligand, and its hapto number is 3. So we say eta3 allyl. So let's do oxidation state, d-electron count, and then total electron count. Oxidation state, DE, and total electron count. So let's start with the oxidation state. The only one that's charged is the allele. Allele has a monovalent ligand plus a pi complex, so it's 3 electrons total. So the allele has a -1 charge. It's just like the ferrocene, it has that one monovalent ligand. You actually see that with a lot of odd eta numbers, is you have multiple pi complexes and then one monovalent interaction. Or a better way to describe it is it's attached to all 3 atoms or all eta number atoms simultaneously, but just it's helpful to think about that one monovalent interaction to help us recall what the charge is. So we have an oxidation state of +1 in this case because we have our ligand charge adds up to just -1, just that allele system. Everything else is neutral. So the oxidation state on the ruthenium is +1. I could write that over here to remind myself. And it turns out that actually I overlooked this. This charge, this complex is actually charged with a +1, and I just missed it. So we have a +1 charge. So if you recall, the oxidation state is the oxidation state here is going to be +2 because what you do is you take charge minus the charge from the ligands. Goodness, I can't believe I almost overlooked that. So you have 1 minus a -1, or 1 plus 1 is equal to 2. Said another way, if we're going to have one monovalent ligand, that is the eta1 of the allele, we have -1 charge from the allele, and the complex has to add up to a +1 charge, then our overall oxidation state has to be +2 on the transition metal to get an overall positive charge of 1 when we're adducted to allele. Okay. So d-electron count, let's pull up our periodic table. So ruthenium, I guess I'm struggling with it's right below iron. So we're at 8. So 8 minus the oxidation state is going to be 6 electrons, 6 d-electrons available. Okay, so we have 6 d-electrons. And then I just want to pull back up my screen. Sorry. Okay, there we go. I was doing Zoom stuff. Okay, so we now have the total electron count. So from ruthenium, we're going to have total electron count. I'm just going to write it down here. I've got space. Total, we've got ruthenium, which is going to give us 8 electrons. CO, which is going to give us 2 electrons. Carbon monoxide's a Lewis base. It's just providing the lone pair would otherwise be neutral. PPH3 is going to give us 2 electrons, but we have 2 of them, so we get 4 electrons. And if we have 4 electrons there, what do we have left? Allele. Allele is going to give us 3 electrons. Goodness, is this right? This doesn't seem right. I should know. I'm the one doing the teaching. 3, 4, 2. Oh, charge. My goodness, we haven't looked at a charged one before. So we have to do the charge, which is going to be, and we have to subtract the charge. So we add everything up, but we subtract the charge. So that's going to be a negative version of +1. So 8 plus 2 is 10, plus 4 is 14, plus 3 is 17, minus 1 is 16 total electrons. My goodness, we haven't looked at enough charge complexes yet in this class. So can't forget the charge complex. That's going to affect your total electron count. You always minus the charge from your total electron count. Okay, sometimes it can be -1, so I don't want to just say it's always positive or some general rule. So we've got 16 electrons total, 6 d-electrons, an oxidation state of +2. The charge threw us off a little bit, but otherwise we did pretty well, I think. Okay, let's do another exercise. This is kind of a fun exercise. I found this on the internet. Sorry, let me get some more pages here. Let's see if we can solve the transition metal. What's the TM? What's the TM when you've got a complex like this? And I'm going to draw this with geometry as best that I can. I have a benzene that's a little flat. Line going from the middle of the benzene down to my transition metal. And let's go ahead and put a little awkward diphenylphosphine. So it's like a triphenylphosphine. It really is a PPH3. But we have an eta-6 benzene, or phenyl, eta-6 phenyl. I guess it's not a benzene, it's a phenyl substituent. And then let's go over here with a PR3. It's a p-cyclohexyl, but I don't want to put psi and just have that bother you. And then an H down here. Okay. And we are overall +1 charge. So what's the TM? Here are the rules. We're at 18 electrons. Electrons equals 18. Okay, so if we're asking what's the transition metal, and we know the total electron count is 18, what we're doing is we're solving for our transition metals. That is transition metal electrons plus ligand electrons minus charge equals equals 18. So we need to solve for this value because we know that the charge is equal to +1, and the ligand electron count we can figure out. If we look right here, I don't know how to, maybe I'll use a blue colored arrow because I've got a bunch of arrows here. Sorry about that. But we have a Lewis base interaction. So that's 2 electrons. We have another Lewis base interactions. So that's 2 electrons. And then we've got an eta-6 phenyl. So that's 6 electrons. So I'm up to 2 plus 2 plus 6. Now this hydrogen is actually just like alkyl or halyl. If we push the electrons over and onto the hydrogen, it's not going to be neutral, it's going to be -1 charge. So this is a hydride or an H-. Okay? So with an H-, we now have a monovalent ligand, which is going to provide 1 electron. So we have 2 plus 2. This is a Lewis base plus a Lewis base plus an eta-6 phenyl plus 1. Okay, so that number, let me just check it again. 2 plus 6 plus 2 plus 1 is 11. So we have X, which is our, let me just write it, transition metal electrons, plus 11 minus 1, because you subtract the charge, is equal to 18. And this is this transition metal, this is our neutral atom count. So we'll know exactly what group number that we're in. And so in this case, we have 18 minus 11 is 9, plus 1 is 10. So we're at 10 electrons from the transition metal. Now, the transition metal, I believe they want us to consider, I mean, so 2 and 6 is 8, plus 2 is 10, 11. So we have 10 electrons from the transition metal. Is that right? Did I do that right? Oh, no. Okay, wait. So, oh no, it says that's right. Oh, gosh, I'm screwing something up. I think the number needs to be 8. Somebody is screaming at their computer right now. So it's 2 plus 2. So transition metal. So it's going to be 19. 19 minus 11 is 8. I just did the math wrong, didn't I? Sorry. 18 minus 11 is 7, plus 1 is 8. Gosh, I'm sorry, YouTube, and hopefully just only the only people watching this are the students in my class. 8 from the transition metal. Okay, so this is going to be, I think in these problems that I'm pulling from, they say, hey, just use this row of the periodic table, but we don't have that information, so we would call this iron, ruthenium, osmium, or HS. I don't know. Okay. Anyway, a better chemist would. So clearly I can't even do simple algebra tonight. But anyway, so we could solve, we solved for that when we looked at some new ligands. I guess that was the important thing. You know, maybe people don't pay me tuition dollars to add 11 and 8 around. Okay. So that's one example. I think the answer, they wanted me to use second row transition metals. So they were going to lean towards ruthenium, but that's not the issue. We're trying to do the exercise of counting electrons around metal centers. So let's do another example. If we want to look at the d-electron count, well, the oxidation state is +2 because we have a -1 on the hydride and we have a +1 charge overall on the complex, and then we have a 6 d-electron count because we have a group 8 element minus the 2 oxidation state. Okay, back to the total electron count. Let's solve for the metal again. It's really solve for the TM group number, I suppose. Okay, so we have a metal. This is going to go up to an 8 of 5 CP. The CP's got on one side of it another phosphine ligand. They really like this trick where they've got the phosphine attached, sort of the phosphine ligand attached at 2 spots, one on the aromatic ring as a multi-hapto system, and then another one as a Lewis base interaction. Hydride monovalent ligand, and then 2 COs. So we have 1 electron from the hydride. We have 2 electrons from each of the carbon monoxide ligands, or carbonyl ligands as they're often called, and then 2 electrons from the phosphine ligand, and then we have 5 electrons because we're at hapto number 5, or 8 of 5 CP. This is an overall neutral complex. Okay, so we're overall neutral, and we have ligand count is equal to 5 plus 2 plus 2 plus 2 plus 1. So it looks like 5 plus 6 plus 1, that's equal to 12. 12 electrons from the ligand, and we need to get to 18 electrons total. So I believe that we have 6 electrons from the neutral TM, and then group 6 is going to be chromium, molybdenum, and tungsten. Chromium, molybdenum, and tungsten. And we could do a total. We could do an oxidation state count on this. We get charge from the hydride and the CP. So the oxidation state to make this overall neutral is +2. The d-electron count is then 4 d-electrons on the metal center. Okay. Let's see. I've got one more good one, and then we'll call it a night. Let's do this metal complex. We have a metal. Let's add some wedges and dashes just so we get comfortable with them. We actually just treat them like straight lines, but they provide some stereochemistry. All right. Have a nice bipyridyl system. Okay, and as just like any good professor, I picked the hardest one to draw last. Okay. So we have here a combination of monovalent ligands, and we have 4 monovalent ligands, and then we have 2 Lewis base ligands. The Lewis base ligands come from the nitrogen atoms. You can think about them as providing their lone pair over, but if it just fell off, we would have a neutral, what's called bipyridyl system. So these are Lewis base ligands with 2 electrons each. Highlight that there. And then we've got a bunch of monovalent ligands here. I have 1 electron each. Okay. So why are those things monovalent? Well, the chlorine we've seen before, but anytime for the maybe the harder ones to see are this one, and this one being monovalent. Oh yeah, the chlorine I guess wasn't the hard one. I mean, it's not the hard one because we've seen it before. It might still be hard because you're catching up, and that's okay. But anytime we've got a carbon directly attached to a transition metal, if we dump the electrons onto the carbon atom, we have a lone pair. And if we already had 3 things attached to it, then we have a carbon with 3 groups attached to it and a formal charge of -1. Okay, so that's a monovalent ligand, just like a hydride or a chloride or what have you. So it doesn't matter that it's an aryl system or if it's a CF3 group, they're all monovalent ligands. So we have 2 electrons times 2 for the Lewis bases, and then we have 4 electrons on the monovalent ligands. So our ligands provide 2 times 2 is 4, plus 4 is 8 electrons. We have to get to 18 electrons total, right? Need 18 electrons. We're overall neutral. So that tells me that we then need 10 electrons from the neutral transition metal. And if that's the case, we have our group 10 elements, which are everybody's favorite nickel, palladium, and platinum. Okay, and if we did other things, if we look, we have, it looks like, golly gee, is that palladium +4 or nickel +4, whatever. The transition metal, the oxidation state is 4 because we have 4 monovalent ligands, and the d-electron count is equal to 6 then. As we take the oxidation state and we subtract that number from the neutral atom count, which was 10 in this case. Okay, so a lot of counting electrons. It's a great way to start the transition metal electron, transition metal reaction unit. It's just kind of looking at metal complexes. I really don't want us to do too much pushing arrows this week in this module. Instead, just maybe open up the back of the book and just start picking out metal complexes and seeing if you can determine the 3 things: the total electron count, the oxidation state, and the d-electron count. Okay, perhaps in the future we'll look at the alternative method of counting using the oxidation state to assist with the counting. That actually affects how the monovalent, divalent, trivalent electron counts add up. They actually just add up by 1, and then the electrons from the metal gets offset by the oxidation state, so it decreases to compensate for it. It's 2 ways of getting to the same answer. I kind of like the neutral atom approach myself. That's how I've learned the ligands to be. But the oxidation state is definitely helpful because you bake in the oxidation state with the calculations, and you also have a more realistic idea of how many electrons you're getting from these negatively charged ligands. Okay, advantages either way. Learn one, get good at it, and then look at the other one. All right, have a good night, everybody.